Hello everyone, welcome to the Borate Fusion webinar. My name is Alain Chantal, I'm the Global Product Manager for the Catanax brand. I will quickly show you what are the company and what are our product before giving the microphone to my colleague Benoit from the application lab. Let's start. In this webinar, we will cover the best sample preparation technique for XRF and ICP analysis. Catanax is based in Quebec City in Canada, where we have our manufacturer and R&D facility. We have founded this company in 2002, my colleague Mark, Pierre, and I. It's in Canada, so people imagine this kind of very nice pictures with the the beautiful snow, where in fact for us it's sometimes a bit of a nightmare, but it's part of the charm of the country, I guess. So what is fusion? Fusion is basically having a sample, in this case, I mean, it's just a piece of copper here, that we put together with a flux, so basically a salt, into a platinum crucible. The instrument is then fusing those mixtures together, and it makes beautiful pictures like that, where we cast the material into a mold made also of platinum. The result to achieve is obviously to convert the samples into glass beads for XRF or into an acid solutions for ICP analysis. The first instrument have been introduced by Catanax in 2002, so now 19 years ago. It was the first low-power electric fluxer in the market, so a very unique aesthetic and design on a very compact instruments. Since then, obviously, we got the first evolution of our product in 2010 to get the prime versions, and then the current instruments that we have on the market. So the K1 Prime, which is still available, the X300 that we can have in 1 or 2 or 3 position that I will explain a bit later, and the X600. One important aspect of our instrument is our heating elements are impervious to flux, which is a unique features. So basically, if you have projections of your mixture, so including the flux that goes straight into the heating elements, they will be protected against that. We also have the dynamic temperature profile control, which means an independent control of each heating element. You need that to be able to reach a uniform temperature all across the furnace. So basically we can heat up more at the extremity of the furnace and less in the center. It also means that if one day one heating element fail, as example this one here, the other one beside will be able to compensate. So that doesn't stop you to use your equipment. We also have the connectivity and our very well-known bulletproof reliability, thanks to the silicon nitride protection, obviously, and other components. We also have the remote diagnostic on our instruments. We will now move to Benoit directly from the Catanax application lab in Quebec City.
Thanks for the introduction, guys, in this first part of the webinar. So I will continue now directly in the Catanax laboratory in Quebec City. I will show you in the next minute the real aspect of Borate Fusion. I will show you the manipulation, and so you can be more familiar with this technique. Before going further, let's take a look back at some theory. I'll introduce a little bit the big lines of fusion. I want to go a little bit deeper. Historically speaking, some scientists discovered that you can use molten alkaline salt to use it as a solvent to digest sample. Over the years, we developed new product. We discovered the nice characteristic of other type of fusion flux. And at the moment today, we will use a lithium borate flux, as you can see here. It's still a salt, but you can see that for the purpose of XRF and create a solid sample, This flux has the particularity to be a glass matrix. So you can have an idea of the molecular distribution here. When we melt this flux and mix with a sample oxide, typically we will see together that the sample needs a specific requirement to be compatible with this flux. So we will talk about oxide, different pure oxide or mixture of it. You can have an idea of the different powder here. And both mixed together at high temperature will give this kind of complex molecular distribution, where the sample, the element of the sample, will introduce the glass matrix to end up with solid specific composition glass bead. It's possible to obtain glass bead, but it's also possible, we will see it today during the manipulation, that you can form this complex glass matrix and pour it into a solution to create a liquid sample instead of a, for ICP analysis, instead of a solid sample for XRF. This next chart shows you an idea of the fusion process itself. So we will mix flux and sample together. We will start heating. At some point around 5, 6, 7 degrees Celsius, it can be possible to have oxidation reaction. We will see it further, but this is to illustrate this phenomena. If we continue to heat until a point when we reach the melting point of the flux will act as a solvent on the sample and start to digest it. We will induce movement of the crucible to digest faster until a point where an homogeneous mixture is produced, where we will pour it in a mold for solid analysis or directly in liquid solution for liquid analysis. Cool down. When it's glass bead, we need to cool it down, of course. So different cooling stage here until we obtain the desired product. So what we will do now is I will bring you directly in my fume hood to show you more manipulation. So you can put your safety glass and lab coat, because you should be inside of my fume hood right now. Let's discuss a bit about the container used to make fusion. Molten borate flux is one of the most aggressive material on Earth, if we can say it like that. So you need a container that will resist this aggressive reaction. This is why we will use noble metal like platinum gold alloy, which will resist to this reaction. Not much other type of container can be used in fusion, and most of them will be affected and will be destroyed slowly. Platinum, even the high cost, is still one of the best options. And keep in mind that whatever happened with your platinum, it will always worth money at the end. So you can sell it back, whatever the state, to have your money back and just buy other ones. So it's much less expensive that it can look like. Let's take a look at the different sample. What type of sample is well adapted for fusion? Fusion is it's a very aggressive type of digestion. So this is why we will use it for different type of difficult matrix. We talk here about refractory materials. We have a couple of examples of sample here. I can show you. We have a kind of catalyst sample here, where we can be interested to look at different element inside this refractory matrix, which is usually made of alumina, silica, difficult to digest with typical techniques like acid digestion, for example. Ceramic pieces here, an example. Ceramic is made of difficult material to digest as well. But we can use it for a lot of different other applications. I have a couple of rocks here, concrete sample. We can use it for people doing glass, interested in glass composition. It can be used in different mining activity, nuclear decommissioning, nuclear activities, and so on. Fusion have the advantage to be used for multiple type of sample. It's possible to make metals, but there is some important aspect to consider with metal. and one of it is only that it's not compatible with flux. So if you want to digest a metal, it will not just combine and distribute into the molten flux. It will remain undissolved. This is one problem. The other problem is that it can alloy with platinum and eventually create problem. A good point is that it's very easy to detect metals. Metals shine, as you probably know. So when you have a powder sample of metal, I will try to show you here at the camera. Hope you can see well, but you should easily see some shining aspect. If your sample shines like this, you should not treat it directly because you can have problem. You can ask help to people like us who will indicate you the best approach and method to use with these metal. On this slide, we can see a few examples of oxidized sample and metallic sample to help you to make difference between both. You have a few examples of different sample here, but what I want to bring your attention to is the aspect of this powder. It's very tan, most of the time pale color, no reflection. So it's a good indication that a sample is fully oxidized. On the other side, metallic sample, pure metals, alloys, sulfide, each of these powder will show you a little shiny aspect, as we just saw in a few minutes ago. As you can see here, this is the kind of result that can happen if pure metal is treated directly without any oxidation during the fusion or before the fusion. The final aspect I want to discuss is related to the flux itself. We have an example here of 50-50 lithium tetraborate, lithium metaborate flux. We have a little proportion of lithium bromine in this one as a non-wetting agent. Non-wetting agent will help to release and avoid sticking of fusion mixture. It will help a lot to keep minimal the maintenance on the platinum. It exists a lot of different proportion between lithium and boron. It's not always easy to have a good idea for people beginning in this area. So I will try to give you tricks to have a better idea on this aspect. I have a chart here called the chart of oxide solubility. You can see that it's pretty similar to a periodic table of element, separate in 3 different color code. So we will associate these color to the element present in your sample. In the middle here, you have the flux scale from pure lithium tetraborate to pure lithium metaborate, and the 50-50 blends, as I just show you in a fume hood in the middle here. What is important to keep in mind is that a type of flux will be better adapted to a type of sample regarding the optimal solubility, optimal fusion condition. If we take a quick example, let's say your sample is mainly made of the red groups here, the alkaline herd element. The red element will have the optimal solubility, the best behavior when the flux will be higher in lithium tetraborate proportion. At the opposite, and we see this very often, sample with a high composition of silica or alumina, which are blue element here. The blue element have an optimal solubility and behavior in fusion when the flux is relatively high in lithium metaborate. We see very often people using lithium tetraborate with silica or alumina, which is not a good match. For the transition metal or sample made of equivalent proportion of red and blue, we will focus on the middle here, so a balanced flux, 50-50 in this case. On this slide, we have theoretical value of solubility of different elements in different type of flux. So for each element here, you have lithium tetraborate on the left side, lithium metaborate on the right side, and you can see how much grams of sample you can digest in a fixed amount of 6 grams of flux. If we take silica, silica is very popular. If we use pure lithium tetraborate, you can see here that you can not digest really more than maybe 0.6 grams of sample in 6 grams of flux. If you use pure lithium metaborate on this side, you can digest up to 1, 2, 3, 4 and more grams of silica in 6 grams of flux. So the difference is very huge. You have example here of other element, combined element. If you can see calcium alone versus calcium sulfate, the gypsum sample, there's a huge difference in solubility behavior. Okay, enough boring theory. We will now prepare a real sample. I will propose you today a cement, Portland cement sample, classic final product of cement plant. This kind of material will be used in real concrete buildings and structure. So it will be very important that the composition of this cement is very precise because it will affect the physical characteristic of the concrete after. And of course, we don't want to have bridge falling down on our cars. So it will be very important to have a good composition of this kind of sample. We will prepare fusion beads, and we will also prepare a solution for ICP analysis with the same sample. So I will prepare right now 100 milliliters of dilute nitric acid that I will transfer in my Teflon beaker. Add my magnetic stirrer and put on the side for later operation. So I will take my platinum, my sample, and I will transfer right away to my friends in the laboratory that will help me to automatically weigh the flux. It's the Catanax Flux Spencer automatic weighting machine and can be used in different mode to weigh fixed mass or ratio. I will use ratio today because I have a fixed ratio calibration on my XRF. So this will help me to be less precise on the amount of sample because this little machine will compensate for the weight of the sample and automatically correct for it. You will see in a moment. So we will try to dispense a first shot of flux. I don't know if you saw, but it automatically tear. All the steps are automated. So now he asked me to add a sample. I will use approximately 0.7 gram. It's only because it's related to the size of mold I will use during the fusion. So 0.7 grams of sample, that will give me approximately 7 grams of flux. That will be good to complete my 32 millimeters mold. So my sample is weighted. You can see I'm not exact, but if I continue here, he will compensate for this non-precise sample weight and will adjust the remaining amount of flux to reach my 1:10 ratio. It's on the coarse dispensing mode right now. It will switch to more optimized dispensing mode until the point where we reach the goal. There is many parameters to optimize on this instrument to make a compromise between speed and precision. So we will try to reach 5.3710 in this case. It will switch to more precise mode now. It's done for the weighting. I will take my crucible and mix a little bit. It's always recommended to mix the flux and sample together. This can have a huge influence on the fusion digestion by after, so we mix a little bit like this. Some sample are more sensible to the proximity between flux and sample, so just keep this in mind. We will now transfer to the instrument itself, where we will just put in place everything. I will open the door. Put my mold here. The crucible with my product for the fuse bead. The other crucible I prepare with a little bit less of flux, another type of flux for the solution. We can provide more information on this kind of preparation if you are interested. I will move away the crucible holder to put the solution I just prepared previously. I will put down here in the beaker pans. You will see it later. Bring back the holders, and I will be ready to start the fusion. Let's take a look at the display now, where you can see all the different icons. It's very visual, very easy to have an idea what is the purpose of different buttons. What we'll do now is to create a method that we will use for our different samples. So I will copy. Yes, I want to copy. It will create another new methods following an empty space in the list of method. You can enter up to 32 methods if I remember well. So I will unlock the instrument to give a very original name to my method, and we will see together what it's all about. So we have a simple case here where we want to reach high temperature quickly, 1050 here. So the closed furnace will wait for you at this temperature. We will hold it for 1 minute and 30, just the time that everything melts very good before moving. You have up to 6 different heating steps where you can change temperature, change the time, the motion of the crucible, everything. In this case, we will use typically only 3 out of this 6 steps because we want a very simple method. At step 5 here, we will start to induce motion to the crucible. So we have the angle here, the speed of agitation, and the duration. So 5 minutes, 20 degrees angle back and forth at 100% speed. The last heating step, we will stay 1 minute and modify a little bit the angle of the crucible. We want here to release bubble if bubbles create during the fusion, and reach higher level in the crucible wall, for example. When it's done, it will be the pouring step. We have default value of pouring here related to the pouring speed, the position of the crucible, and finally we will enter in the cooling step. First cooling stage at ambient air for 1 minute, following by the last step, the second cooling stage, where we will force air with blower to cool down the beads rapidly. In 5 minutes, we will be able to handle the beads and put on the XRF. So we are happy with that. We just save, come back on the display, and we will be ready to press start. And I will show you the movement of the crucible, just so you have an idea. Normally you close the door, of course. I will sacrifice myself today so you can have a better point of view. Door opens, crucible go inside, and close down. I guess you just observed that the light transfer from blue to red indicated that the instrument is under working now. So it's a visual indicator to tell to the people to not touch and easy know the status of the instrument if you are far away in the room. So everything is inside the furnace now. We will be able to follow the status of the method by following the vertical red bar on the display, which will show you how much time it remains and where you had at the different step. Of course, we introduced the cool crucible holder inside the furnace. It dropped the temperature a little bit. The red value you can read here, and it will slowly come back to target temperature on the bottom here, and where the first step will start. During the time the fusion is going on, we will look at different analytical impact and advantage of fuse bead compared to other technique. In this case, we will compare two solid preparation, press pellet, which consists in pressing a powder sample and present directly to the XRF compared to the fuse bead. You can see here typical kind of calibration curve you can obtain with press pellet and fuse bead. You can see quickly that you have more precision, more accuracy with fuse bead. The difference in this analytical quality is mainly due to two factors. The first one is the particle size effect that can be observed in press pellet. Depending on the particle size of your sample, this will directly affect the intensity of a determined element. Particle size affect press pellet because the sample is ground and will end up with a certain particle size. And this particle size can vary, and if it varies, it will vary the intensity of any element. In fuse bead, this aspect is completely eliminated because the sample is not on particle anymore, is digested and transformed into an atomic state where no more particle size effect will influence the quality of result. Second interesting effect is the mineralogical effect that affect the quality of press pellet. Here in the illustration, we show the results of calcium element coming from different matrix, different type of sample, and we try to regroup all that in a single calibration in press pellet. As you can see, the result is not that good. But on the right side, if we take separately all the different calcium form, we end up with a relatively good result. The reason for this is that the signal of calcium will be different depending on their direct neighbor in the matrix. In fuse beam, the calcium, whatever the initial form, will be reduced to an elemental calcium in the glass matrix. This means you are able to combine and align calcium signal from different sample on a single calibration. A big advantage of fuse bead here compared to press pellet. Press pellet, you will need a calibration for almost every element in different matrix. In fuse bead, you will be able to keep minimal calibration due to the specificity of the technique. On the solution side, advantage of fusion will be mainly related to the efficiency of digestion compared to acid leaching. We have some data here that we took into a scientific publication here, where we can see the difference of recovery between acid and Borate fusion in different type of sample. You can see here that the recovery of strontium in soil and sediment are not as good as Borate fusion. The reason is that acid leaching will not completely digest the matrix, and some strontium will remain trapped in undissolved particle. In Borate fusion, we reach a complete digestion, so we will have recovery that meet our expectation. The cement case was not illustrated here because if you look deeper in the publication, the post-operation and solution will influence the recovery. So we can see here that it's approximately equivalent. We are in the last second of the heating step. I will move the camera to show you the pouring. Most exciting moment of the webinar. This is it. So we have the fuse beads on the left side and solution on the right side. You can see on the display that we just entered in the first cooling stage for the fuse bead. For the solution, if you do only solution, you will be able to grab the beaker and finish the dissolution on the side on the hot plate. Creating a piece of glass is not always easy, and you will have to follow some basic rule of the glass chemistry. Two main problems can happen when you make a fuse bead, which is cracking or crystallization of your glass. Some similar reason can lead to the different problematic. For example, undissolved particle can lead in cracking or crystallization depending on different factors. Cooling parameter as well can lead to cracking when we talk about thermal shock. Cooling can be a problem and lead to crystallization when it's too long and let the time to create nuclei and spread into a crystallization. If we look for other reason for cracking, sticking to mold, we see this relatively often. If it sticks too much, it will create a lot of tension at cooling and can lead in cracking. We talk here about the lack of non-wetting agent or typical element in your sample that can increase naturally the sticking of the fusion mixture. Microcrystallization, sometimes it can be difficult to look at naked eyes, but it will be a defect, a local defect of the glass that can eventually cause cracking. As you can see, all this will be related to tension in the beads and eventually lead to cracks. Crystallization, we have external factor. Some fluxer will not be very well protect against environment, and a cooled airflow or little dust landing on the beads during cooling can lead in crystallization. Glass chemistry, we look at this a little bit when we talk about the flux earlier. If you don't have a good match between your flux and sample, you can create crystallization by the wrong glass chemistry of the mixture of both. Mold imperfection. Mold surface is very important to keep clean for XRF reason, but also because default in your mold can be a starting point to align the molecule in the fusion mixture and start crystallization. Fusion is now completed, so we'll be able to open the door, take the fusion beads here. I will show you better in a few minutes. I would just bring your attention on the interior of the crucible. This is what it looks like after a fusion when you have perfect fusion condition. So it's pretty clean, no residues. You will be able to use it right now on the next sample without any problems of carryover. And this is the same thing normally with the solution. Here again, visually nothing. Maybe a simple light cleaning in dilute acid solution will be enough before doing your next sample. I will move the crucible holder away. Take the Teflon beaker, and I have my solution that I will show you better as well in a few seconds. I can show you better here the fuse bead obtained. So no undissolved particle, no visual defect. This is the kind of beads we want to reach. That will be optimal result on the XRF. For the solution, I will transfer right away in a clear container so you can have a better idea of what remains after 5-10 minutes of stirring. And it's already fully dissolved, so you will be ready to complete the volume and analyze this on ICP. I hope this presentation will help you to better understand the principle of fusion, and maybe you will be interested to know if this can be useful for your daily operation. We here at Catanax offer free method development services that engage nothing for the customer and will give them a very good idea on how kind of result they can obtain with the type of sample they work with. If you are an actual fusion user, it's possible for us, we have an ICP or XRF, it's possible for us if you send us a reference bead to replicate your actual fusion condition. So it will just make it easier for you because we can reach a point where no new calibration will be needed, and we can replicate your fusion with all the with all the flexibility that offer the software. We are able to reproduce a lot of fusion condition if you are an actual user. As you can also see is that we try to adapt to the present world health crisis and use different video tools to make live demonstration like this. We can always directly connect with different customers if they need more closer explanation and video support with the process of specific type of sample really related to fusion. So that completes pretty much the part of my presentation. I hope you appreciate the tour. I think we will be ready for the Q&A session now. So if you have any question, you can write it down right now, and it will be a pleasure to answer to you.